Hi there, so this video is on section 5.8 and we are thinking about integration and how we can use what we learned in section 5.7, which was where we learned the derivatives of the inverse trig functions. So in this lesson, we're not thinking about integrating the inverse trig functions, like we're not coming up with the antiderivative of each of the inverse trig functions. We're not doing that in this class, but we are going to look at broadening and adding to our toolbox of functions that we could integrate that we weren't able to integrate before. And this is our final lesson that's adding to kind of that portion of our integration toolbox. So all of these formulas follow from the derivatives of the inverse trig function. So they probably look familiar to you. Now I have the formulas written in a slightly different way. So integrals involving inverse trig functions, right? So where the integral ends up being equal to, the antiderivative ends up being equal to arc sine, arc tan, and arc secant. And if you notice, there's only 3 formulas here. And that's because arc sine, arc tan, arc secant, if you remember their derivatives, and then the derivatives of like arc cosine, arc cotangent, arc cosecant, we're all just the opposite signs. So really we can think about integrating and just using arc sine, arc tan, arc secant, and then just thinking about taking the opposite, like if there is an opposite sign, like treating that opposite sign as basically a constant that would be multiplied by the antiderivative of the integrand. So the formulas that I'm giving you are slightly different and maybe a little bit confusing to look at from the textbook, and I want to explain those. So for each of these formulas, we're assuming that u is a differentiable function, and a is a constant that's greater than 0. Okay, so looking at this, you're like, why are there u's and then why do we have a dx there? And the reason is I think that the formulas written in this form are easier to apply, like thinking about applying, than they are in the textbook form, but they are equivalent, and I want to show you why. So like if we were to think about letting u, or talking about u prime, notice in my formula in each of these in the numerator there's a u prime. So if we were to think about u prime, well, u prime would be du over dx, right? Just different notation. Which then, if we were to use algebra and think about multiplying by dx on both sides of this equation, we would have u prime dx. So notice in the textbook formulas, there's just a du here for the differential, and that's because u prime dx is equal to du. And again, the reason that I'm showing you the formulas this way is that I think that they are easier to see how they're applied and make sure that they can be applied in looking at that. So first, why don't we look at that first formula, which says that the integral of u prime over the square root of a squared minus u squared dx is equal to arc sine of u over a plus c. So we're going to verify that arc sine of u over a plus c is actually the antiderivative of the function that's in the integrand. And the way that we can do that is we can think about differentiating with respect to x, arc sine of u over a plus c. And you are welcome to pause the video right now and you can try it on your own and then see if we end up with the same thing. We should be showing that ends up being equal to u prime over the square root of a squared minus u squared. But again, you can just follow along. Okay, so thinking about the derivative of arc sine, right? We have to think chain rule for finding the derivative here because we have outside function And then we have inside function, and that plus c, the derivative will just be 0. So thinking about the derivative of arcsine, we'd have 1 over the square root of 1 minus whatever the argument is, so the u over a squared, and then we need to think about multiplying by the derivative of u over a. Well, a is just a constant, so you can think of that as like u times 1 over a, which the derivative would be u prime over a, would be one way to write that. And then simplifying, we would have the u prime in the numerator, which is what we wanted, and then if we can pull the a out front of the radical there, and 1 minus u squared over a squared. And then now it's algebra to see if we can get that to be equal to the u prime over the square root of a squared minus u squared. So if we thought about getting a common denominator for what's under the radical, we would have the u prime over a times the square root, so that would be a squared minus u squared over a squared. And remember, we said that a is a positive constant, a constant greater than 1. So then when we take the square root, and we're thinking about applying the exponent property, which follows and is then a property of radicals, right? That the square root of a over b is equal to the square root of a over the square root of b. So this will actually simplify to be u prime over a divided by a times the square root of a squared minus u squared. Okay, and then we're almost there. That just ends up being 1, right? That cancels. So then we have u prime over the square root of a squared minus u squared. Okay, so that checks. We're able to see that, yes, the derivative of arcsine of u over a plus c is equal to that integrand. Okay, so we've differentiated, or sorry, not differentiated, we've integrated functions that are fractions before, right? So like to integrate 2x over 9 minus x squared, you can do a u sub, and then integrate from there. Like we have our formulas, right, that we can integrate that function. The second one, we would also be able to do a u sub, and it will work out. And then number 3, it looks so similar to number 2, but if you tried to do a u sub, you would be stuck. Like this, before us learning the derivatives of the inverse trig functions and talking about the formulas that were on the first page, like we wouldn't be able to integrate this, but we are now. Okay. So we're going to have to use one of the formulas above, and we think, okay, well, what does this kind of look like? And I see, okay, 2 over the square root of 9 minus x squared. So going back up here, I'm like, okay, square root of, it looks probably the most like that first formula, right? That was equal to arcsine. So I'm going to paste it down here so we can reference. Okay, so if we're trying to integrate 2 over the square root of 9 minus x squared dx, let's think about the different parts of this integral that would match up with this formula. So the way that this is written, that means that u would be equal to x, and therefore u prime would be equal to 1. And we could say that a would be equal to 3, right? 9 can be written as 3 squared. So that 2 can actually be pulled out, right? And we can think of this as 1 over, the integrand as being 1 over 3 squared minus x squared dx. So then applying the formula, we'll have 2 times arc sine of u, which is x, over a, which is 3. And then don't forget your plus c. Okay, so that ends up being the integral, the indefinite integral of 2 over the square root of 9 minus x squared, which we previously were not able to integrate, but now we can. And these are formulas that I will give you for your final exam and the upcoming test. But they are not formulas that you would be given on the actual AP exam. You do have to memorize them, but hopefully you'll be so familiar with them by the time that comes around from just using them. Okay, so this is also something you're like, oh, your instinct, because you're not necessarily working in a section all the time, right? That is integrals that equal to the inverse trig functions. You're not always thinking about using these formulas as your go-to. So like if I were just presented with this integral, I would think, okay, I can't use power rule. Like I can't rewrite that easily to use power rule. And then I think, okay, well, can I do a u sub? Well, what would I let u equal to? I'd probably want to let u equal to the denominator, but then the derivative would be 2x, and that wouldn't cancel anywhere. So we can't do a u sub. So then I think, okay, well, this does kind of look like the derivative of arctangent. So referencing the formula from above for the integral that's equal to a version of arctangent, I'm going to come down here, and that's from me knowing the derivative of arctangent, right, is 1 over 1 plus x squared. So pasting that so we can reference. Here, I'll put this, whoops, didn't mean to do that. Just moving this over so we can reference. Okay, so let's think about each part here. So u in this case would be equal to x, which means that u prime would be equal to 1, okay? And a would be equal to 4, it looks like, right? Because 4 squared would give us 16. So we can think about pulling the 7 out front of the integral, and that being 1 over, just to make it match up. This step is not required. But if it helps you to visualize, then go for it. Okay, and then it's just applying the formula. So the 7 will be there, and then 7 ends up being multiplied by 1 over a, so 1 over 4. So we'll have 7/4 times arctan of x over 4 plus c. Don't forget your plus c's. Just going to move this. This is like side work for me. And you don't have to write out those values. It just helps me organize my thoughts. Okay, so this one, you would probably want to try u sub at first. And you'd be like, I'm stuck, right? Because the exponents, the reason being because the exponents here are not the same. So if you let u equal to either e to the 2x or e to the 4x, right, it's not going to cancel with the e to the power that's left, okay? So that doesn't work. It doesn't look, you can't really, you can't split this up and use any sort of like power rule or rewrite it to be able to just integrate e to a power. So then you're like, okay, well then it does sort of, kind of look like the derivative of maybe like arctangent again. So again, referencing that formula and thinking about, okay, well, u would be e to the 2x, right? Because e to the 2x squared would be e to the 4x. So e to the 2x, and that means that u prime would be e to the 2x times 2. Okay, and then a would be equal to 2, since 2 squared is 4. Now here's the thing. If u prime is equal to e to the 2x times 2, or 2 times e to the 2x, we have an extra 2 there. So what we could do in order to apply the formula and have the complete u prime there is we could think about multiplying by a version of 1. And the version of 1 that we could multiply by is, how about 2 over 2, so that we can think about having that 2 in the numerator. So we can rewrite the integral. We don't need the 2 in the denominator, but we do need that 2 in the numerator, so 2e to the 2x, right, over 2 squared plus e to the 2x squared dx. So the 1/2 will be there, and then applying the formula, well, 1 over a would be 1 over 2, times arctan of e to the 2x over 2, and then plus c. I'm just running out of room here. Move my side work over. Plus c. Okay, so to finish simplifying this, that would be 1/4 times arctan of e to the 2x over 2 plus c. There we go. So it's kind of, you think about trying one of these formulas, or thinking about one of these formulas, whenever you can't do power rule, you don't know any other derivative rules that follow, you can't do a u sub. I think it maybe that, because it's the last integration formula we cover, maybe that's why it's the last thing I think of doing. Okay, so for this one, again, like thinking about, like, could I do a u sub? Nope. Could I somehow rewrite this? Nope. Okay, so then thinking about the derivatives, I'm thinking about this kind of sort of looks like the derivative of arcsecant. So if we go back up here to our formulas, I'm going to copy and paste. Yep, I'm going to copy and paste the formula that has arcsecant in it so that we can reference. Okay, so what I'm seeing in here to apply this formula is that we would be thinking about, here, I'll put the u up here. So we would be thinking about u as being x, so that means that u prime is 1. And then we would be thinking about a as being 2. Okay, so that 3 can get pulled out front. We would have 1 over u is x, okay, times the square root of x squared minus 2 squared dx. Okay, so now we can think about applying the formula. So we would end up having 3 over 2, because 3 times 1 over 2, times arcsecant of absolute value of u, which is absolute value of x, over 2 plus c. Okay. Okay, this is different. You're looking at this and you're like, I can't rewrite it. Well, not in order to just apply like power rule. and you can't do a u sub, but it also doesn't fit any of those formulas. But it is a quadratic that you could, different ways of rewriting quadratics. So you could do that. You could think about rewriting the quadratic in vertex form by thinking about completing the square, because we do want to get to the form of a squared plus u squared here, so that we use the arctan formula. So we are going to do this by completing the square. Okay, for x squared plus 4x plus 8. So we can think about doing that by, I'm going to group the x terms together. Well, actually, no, I'm not going to group those yet. Sorry, I had a brain fart on completing the square. So I'm going to leave some space between the 4x and the 8. And then now I'm thinking about, well, what the version of 0 that I want to add, because I'm allowed to add 0. So taking 4, dividing it by 2, squaring it, well, we're going to end up adding 4 and subtracting 4. And then by the associative property of addition, we can regroup those first 3 terms, which will factor to be a perfect square because it's a perfect square trinomial, will factor to be a perfect square. And negative 4 plus 8 will be plus 4, which we are allowed by the commutative property of addition to rewrite as 4 plus the quantity x plus 2 squared to help us with rewriting this integral. So now we can think of this as, here, let me copy this. We can think of this as the integral of 1 over 4. I want it to be a squared plus u squared. So that's why I put the 4 first. So 4 plus the quantity x plus 2 squared dx. And then now I am in the form where I can think about applying the formula. So like u would be x plus 2, which means u prime is 1, and a would be 2. And I could think about rewriting that 4 here, so I don't have to rewrite the whole thing. I could think about rewriting that 4 as 2 squared. So then applying the formula, we would have 1 over 2 times arctan of x plus 2 over 2 plus c. Okay. So sometimes you have some extra work. So here's another one where we're going to have to think a little extra. And this is similar to whenever we had to multiply by 2 over 2 in order to have the correct u prime in our integrand. Okay, so if we have 2 over x times the square root of x squared minus 9, you look first, you're like, what can I do? And then you're like, this kind of looks like the derivative of arcsecant. Okay, so this seems to fit that formula where u would be equal to x squared. Sorry, where u would be equal to, yes, x squared. And a would be equal to 3, okay? Except we don't have an x squared in front of the radical, right? Because u should be right here, but if u is x squared, we don't have that. So what we can do is we can think about multiplying the numerator and denominator, right? So multiplying by 1 the integrand, x over x. I'm going to take this integral, okay, and we'll say that this ends up being equal to 2x over x squared times the square root of x squared squared minus 3 squared, just to have it in the form that's easily referenced. Okay, so then the integral, not sure why I'm going that way, would be equal to 1 over 3 times arc secant of absolute value of x squared, which you don't actually need the absolute value bars there since x squared is implicitly positive, over 3, and then don't forget your plus c. So again, this could be rewritten without, like if this were a multiple choice, you probably wouldn't see those absolute value bars as a possible answer. Okay. And then I do want to give us an example. I didn't put any definite integrals on here, so I do want to put at least one definite integral, and then we can do some more together in class. So let's integrate from 0 to root 2, 1 over the square root of 4 minus x squared. Okay. So you're just thinking, okay, well, we can't do a u sub here. This does look like the arc sine formula. So if I come back to reference our arc sine formula, put it down here. Okay, so if we're referencing our arc sine formula, we would see that like u would be x, u prime would be 1, so that's good, and a would be 2. So the antiderivative would be arc sine of x over 2. Don't need the plus c because this is a definite integral, and then we can apply the first fundamental theorem of calculus. So arc sine of root 2 over 2 minus arc sine of, that'll be of 0, and I think arc sine of root 2 over 2, it's going to be pi over 4, and then arc sine of 0 is 0, so it just ends up being equal to pi over 4. Okay, and then I do have a few more examples, but I think I'm going to leave those for class for the definite integrals.